in Applied Physics IISc in March 2018 as an assistant professor. His group is interested in quantum information and quantum computation with superconducting circuits in particular and solid state circuit in general. His current work also involves coupling these superconducting artificial atoms to propagating phonons on the surface of piezoelectric substrate to realize the acoustic analog of quantum optics, quantum acoustics. So with this, I welcome you, sir, for this one workshop. Over to you, sir. Thank you very much.
Thank you, Mahesh, for that introduction. And I want to thank the organizers for this interesting subject, because I am actually a physicist by training, and I get to talk a lot about quantum physics in general. But today is a rather interesting deviation from that. I'll be speaking mostly on the engineering side of how we realize these systems. I'll keep the physics and the maths out of it for a large part of the talk, and I want to pitch it at a colloquium level so that even engineers with no background in quantum physics can follow what is going on. So let us see. So the topic for my presentation is microwave superconducting circuits for quantum information processing. And as Mahesh mentioned, I set up a quantum technologies laboratory at the Department of Instrumentation and Applied Physics in IISc. And I've been there for the last 3 years. Okay, let's see. Yeah, so first let's set the context for this presentation. So we are, as we speak, superconducting circuits, which I'll be focusing on in this presentation, they operate in the microwave regime, and they are the topmost qubits currently in the world, and they have raised to 50 plus qubits, and the processor size that is currently operated is around 100 qubits. And there is a huge race worldwide to build a quantum computer, and superconducting circuits are leading that race. And many big companies have invested in this. For example, IBM, Google have been in this business for more than 10 years now. And Google demonstrated very famously this quantum supremacy with 50 plus qubits about a couple years back. And IBM has come up with a roadmap for 1000 qubits over the next decade. In the last few months, they released this roadmap. Okay, so this is the context in which we are discussing, and what will we cover in this presentation? I'll cover why are microwaves special. So microwaves are quite commonly known to people. They use them, but they have some special properties. So we'll look at what those are, and then how they are used for quantum information processing, and what is the state of the art, and what are some challenges and future goals. These will be the topics I will touch upon in this presentation. Okay, so here's the outline. So I'll first go into a little very cursory basics of microwaves. You will not see Maxwell's equations in my presentation. So I'll keep it at a very basic level. And then I'll do something very similar with quantum information processing, and then go into superconducting circuits and how they work and how we control them and characterize them in the microwave domain. And then finally, I'll present a set of advantages, challenges, and how the future looks for these devices. And at the very outset, I want to say that the future belongs not so much to the physicist, but to the microwave engineer. So that is the larger context of this presentation. Okay, so just to introduce, the microwave spectrum is, of course, part of the electromagnetic spectrum, which has an infinite range in wavelength. Here you can see the frequencies, and this middle range here. Can you see my cursor? Can somebody tell me if you can see the cursor?
Yeah, we can see.
Okay, so this range between around 10 power 9 hertz, that is a few hundred megahertz to a few gigahertz or few tens of gigahertz, or even going up to 100 gigahertz plus. This range is what we typically call the microwave range. And the circuits that we are, and here you can see a whole bunch of bands within the microwave regime. Okay, so L, S, C, X, KU, etc., etc., etc. So superconducting circuits that I'll be talking about, they operate mostly in this frequency range from 2 to 12 gigahertz. So that lies somewhere around this region here, around the gigahertz mark, and they span portions of the L, S, C, and X bands. Okay, So this is the frequency range that we are interested in. Now, microwaves have wide-ranging applications, right from the kitchen to the cosmos. So for example, we use microwave ovens on a daily basis. Cell phones use microwave frequencies. Radar technologies are more strategic applications, higher scale. And of course, we have the very famous cosmic microwave background, which forms the in the current state of the art for cosmology, this forms the evidence for an inflationary Big Bang. So cosmic microwave background is the background wherever you look in space, you see this microwave radiation, which is thermalized at some 2.7 Kelvin temperature. And this is there everywhere. And this picture that I show here on the bottom right corner is actually a picture taken over several years in different solid angles of the space using a satellite. And this is a, yeah. So microwaves are essentially everywhere. And my slides are not changing properly. Okay. Now, microwave technology, which we are interested in, is actually very mature. The first microwave masers were invented back in the 50s, and they have one very important property of microwaves. And whenever I use these terms low and high, I'm typically comparing with visible light. So microwaves have very low energy compared to visible light, and they are roughly 10 to the power of 5 times smaller energy. Now, low energy always means that generating them is not too difficult, but detecting them can also be quite difficult. Okay. So now when I say detection of microwaves, I mean single photons of microwaves are extremely low energy. And we usually have these photodetectors in the visible regime and the ultraviolet and all these gamma rays and all those higher energy radiations can be detected using photodetectors or some sort of Geiger counters. Such detectors don't exist for microwaves. Okay. And highly coherent classical microwave lasers, or the equivalents of lasers, which are technically called masers. And in fact, masers were invented before lasers were invented, and they are readily available. You can just buy them off the shelf, and they're extremely stable. They don't have much drift and very well engineered pieces of equipment. And they have applications to both civilian and strategic goals, as I showed earlier, which means that a wide range of commercially available products are there. So working in the microwave regime is quite comfortable. Then wavelengths of these radiation of this range is in the centimeter to meter scales, and that poses some interesting constraints on what sort of electrical circuits, because these are electromagnetic radiation that we are talking about. So we generate them using some sort of an electrical circuit. We cannot use the simple lumped element LCR components that you can say buy off SP Road or one of these electronic markets in Bangalore, because these LRC components are usually in the centimeter to millimeter scale, and the wavelengths of these radiation also are on that range, which means that these components don't behave as lumped element components for microwaves, so they cannot be reliably used. So we end up using transmission lines in most of microwave theory. Okay. So yeah. Now let's move to quantum information processing. So that was a brief intro to what microwaves are and some relevant properties to our discussion. So first, quantum information processing itself it had some very dreamy beginnings. So Feynman was the first one to pitch for a quantum computer or a quantum simulator. Now his reasoning was that simulating quantum systems on classical computers was a lost cause, because even classical simulations of say molecules binding together and condensed matter systems, these are extremely difficult to simulate. And now if you want to even capture the quantum effects, that becomes extremely difficult. So he said, why not engineer quantum systems to simulate other unknown quantum systems. If you can engineer some known quantum systems, you can probably use them to simulate unknown quantum systems. And this was the sort of the germ of an idea that he planted in the community around the early 1980s. And a lot of work happened on the theory front. All this was purely speculation. No realizations took place for at least 2 more decades. A lot of algorithms were created, and quantum computation as a field of theoretical interest was well established. And as and when these machines were to be realized, they would be specialized machines to solve specific classically intractable problems. And they are not, of course, going to supplant classical computers as a whole. This is a common misconception that people have, that can you do your normal web browsing using a quantum computer? No, that is not the purpose for quantum computer. It's going to solve some specific problems. And the basic unit of such a quantum computer is what is called a quantum bit or a qubit. This is like a classical bit, but with quantum properties. Okay. Some reason, yeah. Now, what is a qubit conceptually? So it's any quantum system where 2 states can be isolated and studied. And it's also called a spin half system. And the states are usually represented by these funny symbols, up and down, or 0 and 1, or G and E, G standing for ground state and E standing for excited state. And a general qubit state is a superposition of the ground and excited states. It is in this aspect that they differ very crucially from the classical bits. Classical bits can be either in 0 or in 1, but here they can be in a superposition. And alpha and beta are in general some complex numbers which have to satisfy this probability constraint that the sum of mod squares of those numbers has to be equal to 1. And naturally, any 2 such numbers can be represented using trigonometric functions. So you have a general representation of a single qubit state as some cosine theta by 2. This by 2 is just a technicality. So if you just take the mod squared of cos squared plus sine squared will just become 1. Okay, so you can always write alpha and beta in this form. And this theta and phi are chosen in such a way that they represent the points on the surface of a unit sphere now in the complex space. Okay, so a single qubit gate. Now, why am I giving this introduction to quantum computing is because I'm going to show how these are realized in practice using superconducting circuits and microwave signals. Okay, and a single qubit gate in quantum computation is basically a rotation of one vector on the surface of the sphere to another vector. Okay, and you have to control basically 2 angles, theta and phi, to reach arbitrary locations on the surface of the sphere. Remember that a sphere is a 3-dimensional object, but the radius is fixed. So there are only 2 degrees of freedom, which is the latitude and the longitude, which are the theta and the phi respectively. And this sphere is also called the block sphere. Now, I have told you that people are running after these quantum computers, but I haven't really told you why. So here is a very simple example. This is not a full quantum algorithm in itself, but a small subroutine of a quantum algorithm in almost every quantum algorithm looks like this. Let us say you have f of x, which is a classical Boolean function over a single bit x. What that means is x can take values of 0 and 1. And f of x also takes values of 0 and 1. So you input some x. If you say f of 0 is 0, f of 1 is 1, that's a Boolean function, which is f of x equal to x. So now classically, if you want to check what the values of these functions are, you have to check it for both inputs, for x equal to 0 and x equal to 1. But if you were to realize this using a quantum computer, you can construct a box like this. I'm not going to explain the box. All I'm going to say is you do some magic, you input a 0, you do some operations on that 0, you get a superposition like the 0 plus 1 by root 2, and that is input into this black box, which I call UF. And on the output of that black box, you get a superposition of 0, f of 0, and 1, f of 1. So in principle, both f of 0 and f of 1 are there at the output in a single evaluation. So instead of doing 2 evaluations of the function, you can evaluate both f of 0 and f of 1 all in one step. And similarly, if you, the advantage becomes even more clear when you extend this to n bits. So for n classical bits, there are 2 power n states possible, right? Like for example, for 2 bits, you have 0, 0, 0, 1, 1, 0, and 1, 1. So this is 4 states. In the same way, if you have n bits, you will have 2 power n states. Now, all 2 power n values of this f of, f of x will be there at the output in superposition. So in principle, you have evaluated all 2 power n values in the single evaluation of the function. So this is an exponential speed up. Now, whether this actually materializes into reality or not is a secondary question, but in principle, using the mechanisms of quantum mechanics, you can do this. And that is why there is a charm to the subject. All right. So now where do microwaves figure in all this? Yeah. Now this was all this was a conceptual discussion about quantum computers. David DiVincenzo in 1995 gave a set of practical criteria for how to realizing a quantum computer, and the criteria are as follows. One, there should be a physical realization of a qubit, because people have been talking about theoretically about qubits, but there should be ultimately a physical realization, and we should be able to read out these qubit states. Meaning, if you prepare a qubit state as a superposition, as I told you earlier, we should be able to read it out and figure out what superposition it is. Then each qubit should be controllable. This is a very basic requirement. In classical parlance, a register or a bit cell, as they call in classical computation, you should be able to set that bit cell to 0 or 1. Okay, you should be able to write. Essentially, you should be able to write into the computer. And these quantum bits suffer from something called decoherence. That is, if you set the quantum bit, there could be an error, and the quantum bit will basically change uncontrollably due to interaction with the environment. This is called decoherence. And we want this decoherence time to be as long as possible, meaning it should happen very slowly. So a long coherence time, it sets the limit on how many operations you can do before the qubit changes sufficiently. And that is an important criterion. And finally, which is the most important in our present context, the architecture must be scalable. Okay, so these are some practical criteria that were given. And to give you a rule of thumb, for a practically useful quantum computer, we need around 1 million qubits. Okay, so I just told you that the state of the art is 50 qubits. So that tells us how far behind we are currently. The efforts are on to scale them up. For example, IBM said they'll scale them up to 1,000 qubits in the near future, but 50 to 1,000 is a huge step. 1,000 to 1 million is going to be even a bigger step. So we have open problems to solve to reach that goal. Okay, now let me now show you the first superconducting qubits that were invented back in the late 90s. Actually, at the turn of the 21st century, in 1999, the first ever demonstration was done by using a single Cooper pair box. I'll tell you what a Cooper pair box shortly. And this was the first demonstration of qubit control ever. Okay, and this was a very landmark result. The coherence of the qubit was very small, so it could not be used as a quantum computer or anything, but it gave people hope that this can be used for building a real quantum computer. And in 5 years' time, massive improvements happened, and this entire field of what is called circuit quantum electrodynamics began thanks to some pioneering work that happened at Yale in 2004. And the circuit quantum electrodynamics is essentially putting this qubit inside a cavity. Okay, and what this cavity does is it protects the qubit from the environment, giving it a longer coherence time. And as I will show you in a few slides, This cavity also gives a very nice way to read out the qubit. So all the criteria that David DiVincenzo gave were now there in place in this circuit quantum electrodynamics architecture. So here, you see in the right side graph, the top figure shows an actual photograph of a chip. So the substrate is sapphire, and on top of it, they have a layer of, in this case, niobium, and these coplanar waveguide transmission line resonators that you can see. In the center, in the zoom in, you have this qubit, and you can see the length scale. It says 5 micron here. So the qubit is about a couple microns in dimensions. Okay. So you can see couple microns is much larger than a natural atom, which is a few angstroms in size. All right. And this circuit quantum electrodynamics architecture has been the game changer in the last 20 years. And all the superconducting circuit architectures that I'm going to talk about are in this circuit quantum electrodynamics architecture, where you have a resonator and a qubit. Okay. So now I'm going to talk about how these qubits are made in labs. So before we do that, let us quickly revise our basic high school physics about spring mass systems. We all know that a spring mass system, or a simple pendulum, it makes harmonic small oscillations. Okay. If you oscillate a pendulum at a very small angle, the oscillations are simple harmonic, like cosine theta and sine theta, right? Now, you can also extend this to more spatially extended systems, like a string that is clamped at both ends, and like a guitar or a sitar string, and you pluck it and it oscillates. And there are a set of normal modes of this oscillation, which all have a harmonic spacing of frequencies. So there is a fundamental, and then there are higher harmonics. Okay, omega naught, and those are set by the speed of sound along this string, as well as the length of the string. Okay, so this is the now the spring mass system is a single mode oscillator, meaning that it has only one characteristic frequency, whereas a string is a multi-mode oscillator which has multiple modes of oscillation. There is an omega naught, and there is omega 1, which is omega 2, which is 2 omega naught, then 3 omega naught, 4 omega naught, and so on and so on. And each of these modes of oscillation is like a spring mass system. It's a single mode oscillator. Okay. Now let us go to, we can also, these are mechanical oscillators I talked about. We can have electrical circuits, and electrical circuits like a simple tank circuit or an LC oscillator is shown in the top figure. We can also have coupled LC oscillators. So all these are quite familiar. I'm not going to dwell too much on those. But how do you realize? I told you that these circuits work in the microwave regime. And I also mentioned that microwave regime is characterized by long wavelengths compared to these LC components that you can buy in the market, which means that these lumped element LC components, which are shown in the left figure here, they cannot be used. So what we typically do in our case is we use transmission lines or coplanar structures to mimic this behavior. So here is a false color. It's actually a microscope picture of one of the devices I made a little while back. Let me walk you through what this device shows here. So the gray that you see is actually aluminum, and the black that you see is the substrate below. This is the top view of the picture of the device. The black is silicon, and the yellow is, the gray is aluminum. Aluminum, interestingly, many of us don't know, but it's a superconductor at 1 Kelvin and below. So, and it's such an abundant metal and so inexpensive that it becomes a very attractive choice for making superconducting circuits. So 99% of the devices that are made today are made of aluminum. Okay. And here I have shown in the violet here, you see a transmission line, which is just a simple coplanar waveguide. And here you see this blue structure, that is our LC resonator. Now, it doesn't look anything like what components I show on the left. But if I maybe point out the similarities it will strike to you. This left side here is the meandering structure, which is like a coil. Okay. In the coplanar geometry, this is equivalent to a coil, and that forms the inductor. And on the right side, you have these two interlocked electrodes. This is called an interdigital capacitor. This interdigital capacitor will make several appearances through the stock. So this forms a capacitor. It's like two electrodes interlocked with some gaps in between. And these gaps are filled by the dielectric. So they form a sort of capacitor. Now the keener eyes among yours will point out that this is entirely one piece of metal, which means that it is actually a short at DC. So it only behaves as an LC oscillator at high frequencies. And the frequencies for this particular device are around 5 to 6 gigahertz. Okay. So now let's go to the, this was about linear oscillators. So as I mentioned, a pendulum oscillating at small angles behaves as a linear simple harmonic oscillator, and the equation of motion for that will be given by theta double dot plus g by L theta equal to 0. But if you actually increase the amplitude of oscillation, a pendulum is no longer a simple harmonic oscillator, but it's actually a nonlinear oscillator. Okay? So that equation of motion is given by this, and you can see that you can expand the sign for small angles as the lowest order approximation will just be theta. But if you include the first order of nonlinearity, it will be like a theta cube term. So this is nonlinear. And the energy of this system, from high school physics, you know that there is a kinetic energy for oscillation for this pendulum, and then there is the potential energy due to gravity. So those are these two terms. And if you ignore this constant MGL term, this energy of the system is essentially kinetic energy minus MGL cos theta. And in general, for a nonlinear oscillator, the frequency will not be a simple parameter, but it will depend on the amplitude of oscillation. That's a very characteristic feature of all nonlinear oscillators. And that plays a very important role in our quantum circuits. So now let's go into the quantum domain of these oscillators. So far, we talked about linear classical oscillators and linear nonlinear classical oscillators. Now, what in quantum language, how do you describe them? So according to Max Planck, if you take Planck's, the energy of a quantum oscillator essentially comes in discrete units of h cross nu, h nu, where h is the Planck's constant and nu is the frequency. Nu is just the classical oscillation frequency of the oscillator, and h is a fundamental constant of the universe. And the energy of an oscillator can only be integer times the h times nu. Okay. And this physically means that a harmonic oscillator with one resonant frequency, like the simple LC circuit that I showed you, has an equal spacing of adjacent levels. Okay. So basically it has h nu, 2h nu, 3h nu, and so on and so forth. A nonlinear oscillator, and as you go higher up in these levels, the amplitude of oscillation is basically increasing. Okay. That's the classical image that you can have in your mind. Of course, it's not an exact picture, but that helps at this level. And a nonlinear oscillator, on the other hand, will have a different frequency as the amplitude increases. And since frequency is actually the gap between these two adjacent levels, what we now have is that the spacing between the adjacent levels is actually changing. So nonlinear oscillators have enharmonic spectra. Enharmonic meaning they don't have equally spaced spectra, but the spacing between adjacent levels keeps changing as you go up the ladder. Now, those of you who remember your high school modern physics will remember that atoms like hydrogen, sodium, rubidium, when you shine light, they absorb and emit radiation at a certain frequency or at a whole bunch of frequencies, not just one. There are all these levels inside an atom and there are transitions that happen between them. And each transition has a unique signature. And a very characteristic features of feature of these natural atoms is that the various frequencies that you see in their spectra are not harmonic, meaning you don't have some fundamental mode and all the higher frequencies are not some 2f0, 3f0 like that. They are very complicated, relations among them, but they are not harmonics. So what we now say is that these natural atoms can be simulated. Remember Feynman, the goal is to simulate natural quantum systems which are made of natural atoms, and we can simulate them using nonlinear oscillators. Okay, so that's the central idea. And so we have to make nonlinear oscillators now using superconducting circuits for them to be used as artificial atoms. Okay, so this is just a summary of what I have said in words all this while, that you have harmonic and anharmonic quantum oscillators, and in the harmonic case you have a parabolic potential which goes as mgl theta squared, and you have equal spaced energy levels, whereas in the enharmonic case you have this potential which is a cosine theta. Remember that cosine theta can be approximated as theta squared in the small angle approximation, and that's what gives you the harmonic approximation. Whereas here, if you take the full cosine theta potential, the energy levels are no longer equally spaced. So how do you then make a nonlinear oscillator? So we know how to make a simple LC oscillator. If you use a simple linear inductor and a linear capacitor, you get a linear LC oscillator. What if you use a nonlinear inductor? That is what we typically do in the superconducting circuits. Nonlinear inductors can be made thanks to superconductivity. This is one of the main reasons why superconductivity and superconducting circuits became so popular. The ease with which you can make a nonlinear inductor is unparalleled. And there is this effect called Josephson effect, which says that if you have two superconductors with a thin insulating barrier between them, there will be a tunnel current across this barrier, and this tunneling current, which is a purely quantum mechanical effect, will result in this device behaving as a nonlinear inductor. Okay, so if we can make an LC circuit and replace that L with this Josephson junction, as I just said, that will behave as a nonlinear LC oscillator. Okay, and that will have, and interestingly, without going into the mathematics, if you write down the energy of this nonlinear LC oscillator, it has exactly the same energy function. The potential of this is essentially mg cos theta, which is the same as a potential, as a pendulum. Okay, so the physics of this oscillator is essentially the physics of the pendulum. So instead of a simple pendulum, we now have a full pendulum, which is a nonlinear oscillator. Now I introduced what is called the circuit quantum electrodynamics architecture earlier. So let me now tell you how that is constructed. So we have introduced a classical microwave LC circuit in the coplanar geometry earlier. I have also introduced a qubit, which is basically a Josephson junction with a capacitor across it. So this qubit is coupled to a resonator, which is in turn coupled to a transmission line, as I showed earlier. This entire structure is what I am referring to as a circuit quantum electrodynamics architecture. Now, the entire system is probed using microwave tones, and the frequencies of these devices are somewhere between 2 to 12 gigahertz, the mid-range being around 5 to 8 gigahertz is the most common range that people use. And how does the resonator help? It first protects the qubit from the environment. Remember that every resonator is a filter. It allows only certain frequencies to pass through. So that is a filter. So it protects it from the environment, and it also helps you read out the state of the qubit. So here is a schematic that I show, where you have the coaxial cable, which is the equivalent of a transmission line, and you have tones, microwave tones that you can input, and those tones will now interact with this device here, which is the resonator coupled to the qubit, and these tones come out on the other side, and you analyze what comes out. And by looking at the amplitude and phase of the tone that comes out, typically the resonator and the qubit are at different frequencies, slightly separated, and you send one tone which is resonant with the resonator and one tone which is resonant with the qubit, and what you take at the output is only the tone that is resonant with the resonator. Okay, so that is typically what we call the readout tone. Now this readout tone is what goes out and is analyzed for its amplitude and phase, and you will see that this information gives you information in turn about the qubit. Here is the full geometry of the device. Earlier I showed you a cropped version of it. So here you have the aluminum, which forms a ground plane. The ground plane around the device acts like a Faraday cage, protecting the device from electromagnetic interference from outside. And then you have this purple, which is the transmission line, the blue is the LC oscillator, and the red here is our device. And this green here is some control line, which we use to manipulate this device. Okay, so for example, if the readout tone is going here, the other tone resonant with the qubit will actually come on this green line. Okay, so that is the basic architecture. Now, how are these circuits made? We use simple photolithography and e-beam lithography. Aluminum thin film on silicon or sapphire substrates is what is commonly used. Photolithography forms all the coarse features. So in this device, you can see all these features. The scale is given here, it's 100 microns. Everything is in the tens of microns range, so they can be very comfortably fabricated using photolithography, which usually has a diffraction limited, unless you are Intel. In most labs, you can only reach up to 600 nanometers using photolithography. Intel, of course, does some very sophisticated image processing and correction, electromagnetic focusing, and countering the aberration effects and diffraction limits to actually go down to almost 40 nanometers or 20 nanometers, but that is not something that we can do in labs regularly. Okay, and this is just a cartoon to show how we use an etching process. We just take the substrate, put the aluminum on it, then coat it with a photoresist, put a mask, expose the resist, develop it, and then we etch the aluminum so that, and then we can just strip the photoresist and we can form patterns of aluminum on the substrate like this using an etching process. I'm not going to spend too much time on the chemistry of it, but yeah. And then this is the same device without the colors. I want to now focus on the Josephson junction, which is at the center of this device, which I show here in a zoomed in picture. The Josephson junction, you can see the length scale. For this device, the length scale is 100 microns, whereas for this device, it is 1 micron. And so this is 100 times smaller already. We are already magnified 100x. And this central overlapping region between these two perpendicular electrodes, that is where the Josephson junction is. So as I said, it is a sandwich between two superconducting layers. So both of these white crossbars are aluminum electrodes, and you grow a small thin layer of oxide between them. And that's how you form the Josephson junction. And here is the, and for such small geometries, we have to use an electron beam lithography. So the size of the junction is usually 100 nanometers. And so for that, we use electron beam lithography, which is very similar to photolithography, but the radiation that we use is electron beams. And because of that, we can go down to smaller length scales. And here is the process where we first deposit one layer of aluminum, then we grow an oxide, and then we deposit another layer of aluminum at a different angle. And finally, we remove the resist and we have the Josephson junction here. All right. Now, this is about how we make the devices. How do we measure these devices? We need low temperature for them. Why do we need low temperature? One, Josephson effect requires superconductivity. And for that, we need to operate below the critical temperature, which means that we need to have temperatures below 1 Kelvin. That already makes these very niche experimentally, because there are very few systems that can take you down to 1 Kelvin. Helium-4 is the only cryo fluid that we know which can take you down to 1.4 Kelvin. But is 1 Kelvin enough? No. We need to actually reach far below 1 Kelvin, because superconductivity is a sudden transition as far as the resistivity of the metal is concerned. But if you go down, there are other aspects of the superconductor which, like quasi-particle poisoning, etc., which have a slower dependence. So to counter those, we need to actually go to much lower temperatures, say of the order of less than 300 millikelvin. Now, those are temperatures that we cannot reach using helium-4. So we need to immediately bring in helium-3. But helium-3 is extremely expensive. So say a few liters of helium-3 will cost you about $50,000. Okay, so that's how expensive it is. Now, we can reach 300 millikelvin using helium-3, but then is that enough? No, because we need to operate these devices at around 5 gigahertz. Now, why 5 gigahertz? It turns out that aluminum has a TC of 1 Kelvin, which means we need to operate below 1 Kelvin. At temperature of 1 Kelvin corresponds to a frequency of 20 gigahertz. Okay, so whenever you have a temperature, Kb times the Boltzmann constant times temperature gives you an energy scale. Similarly, a frequency times Planck's constant, which is another fundamental constant, gives you the energy scale corresponding to that. And if you do the equivalence, T equal to 1 Kelvin corresponds to 20 gigahertz in frequency. And because of that, we need to operate much below 20 gigahertz. But at the same time, we can't operate at arbitrarily low temperature, low frequencies, which means a frequency around 5 gigahertz is reasonable, which already puts the temperature limits at below 50 millikelvin. If you want to reduce the thermal excitations and the quantum signatures of the device to be manifest. So this is the reason why we need low temperatures, and there is this very you have to use a particular mixture of helium-4 and helium-3 isotopes, and that will take you down to arbitrarily low temperatures, but in practice we can reach up to 5 millikelvin or of the order of 1 millikelvin at most. And that is sufficient to measure these devices. And in summary, all these constraints, including the TC of aluminum, etc., put confines on the available bands in the microwave regime that we can operate, and that is usually the LS, C, and X bands. Okay, that's where this requirement comes from. Now here is a schematic of a dilution cryostat, and you can see that. So you have the blue is the input line. Here is the sample at around 10 millikelvin. All the electronics is sitting at room temperature at 300 Kelvin. So you cannot obviously send a single cable all the way down. Most cables can't even survive the mechanical stress of having such a huge temperature gradient. So we have to break the cable in smaller sections, and special materials like copper beryllium and copper nickel are used for these cables. And then we put attenuators to cut down the thermal noise coming from the higher stages along these cables. And on the output line, because you put so much attenuation, the signal coming out of the device is tiny. It is usually in the attowatt or to a few femtowatt range. So that needs amplification so that you can measure it. So you put amplifiers at various stages. Again, amplifiers add noise, which means that you can't put all the amplification at room temperature because that adds a tremendous amount of noise. Your signal to noise ratio will be degraded. So you have to put amplifiers also at various stages, and doing all this, you can now get a signal at the output which you can measure. And you take this to a demodulating circuit, which I'll show in a minute. And here is the inside of a dilution cryostat. It's basically a vacuum chamber with these copper mounts on which, and you can also see these coaxes, rigid coaxes that you have. And this is the setup for 1 qubit, okay, in my lab. And So here is an outward view of dilution cryostat. This is a picture from IBM of one of their IBM Q labs. And you can see the scale of this lady here. She's say 5'5" and the fridge, of course, it's much closer to us. So it is about 6 feet in scale. Okay, so it is human dimensions. So this is no longer a very miniature, and this has maybe about 30-40 qubits in it. So it's a very tiny processor, not very practically useful, but it's already at a pretty big scale. And this is all the surrounding equipment are its control circuitry. So this automatically conjures up images of bygone era where this is the first fully programmable computer that was made in the 1950s and 60s called the ENIAC. Okay, so you can see that this is all the computer is human scale and all the control architecture, control electronics around it, the electrical controls, in fact, in those days, all that is also, it occupies a full room. So in some sense, in quantum computation, we are still at the stage of the ENIAC. And we don't have anything like the Moore's law, which is predicting a bigger increase. So we'll see. Now, how do we control these qubits? As I said earlier, you just have to, a qubit state for a single qubit is essentially a point on the sphere, and you have to rotate this point. And it turns out, without going into the details again, if you just apply a voltage, a microwave voltage, which has a simple sinusoidal or a sinusoidal voltage with a certain frequency which matches the transition frequency of the qubit, the ground to excited state gap of the qubit, and with a certain amplitude omega and a phase phi, you can prepare very deterministically, you can prepare this state. And this is a fabulous feature. That is, you can, in principle, prepare a quantum state without any problem in the labs these days. All you need to do is apply a certain amplitude. The amplitude controls the latitude on the sphere, and the phase of the microwaves itself controls the phase or the angle phi on the sphere. So this is very easy to do. And here I show how you can deterministically take the qubit state from ground to excited and then bring it back and then do this endlessly, pretty much. All right, so now to summarize, single qubit gates are essentially for a duration tau with some amplitude omega and some phase phi, you apply microwave tones, and this does what is called a gate operation. However, of course, as I said, there is decoherence, which means that you cannot send arbitrarily long pulses, meaning this duration tau cannot be arbitrarily long because the decoherence would have killed the state. And this sets there is a trade-off that you need to do. And this trade-off is usually measured in this quantity called fidelity. And fidelity is a very important parameter which measures the quality of your qubits. And typically, the existing current single qubits that we have in labs, they have a fidelity of 3 nines, 0.999. So this number is a number between 0 and 1. Okay, 3 nines. Now, how does this measure up to what we require? So similarly, you can have 2 qubit gates. If you have 2 qubits coupled to each other, you can also perform these operations on both the qubits. We'll leave out all those details in the interest of time. And the current fidelities of 2 qubit gates are 2 nines. So single qubit gates are 3 nines and 2 qubit gates are 2 nines. And this puts the error rates around 10 to the power of -2. Okay, because 2 nines essentially means 0.01 is the error rate. That's 10 to the power of -2 to 10 to the power of -3. And the required error rates are less than 10 to the power of -8. So we do have quite a distance to go. Now, how do we read out the qubit? I told you how to control the qubit. You just apply a microwave tone on the transmission line with a certain amplitude and duration and a certain phase, and that takes care of where the qubit lands on the sphere. Now, how do you measure this? Now, this is where some, simple signal processing basics I want to revise. So any signal, which is what is called a quadrature amplitude modulated signal. In electrical engineering communication terms. It's a quadrature amplitude modulated signal, can be represented using some amplitude A, which I denote it as if it were a constant, but in general, it's a very slow changing function of time. Compared to this omega here, the frequency of the carrier, which is much higher, say if the carrier is a few gigahertz, this will be not more than a few tens of megahertz. So it's a very slow changing function. This can be now expanded as x1 cosine omega t plus x2 sine omega t. And from measuring x1 and x2, you can measure the amplitude A and phi using these simple relations which follow from this expansion. Now, you can also represent a signal. It's like the phasor representation of electrical circuits in the x1, x2 space. And a signal is essentially an arrow emanating from the origin in this space. Okay. And now this point here represents a particular signal S of t, but I also drew this circle around it with a red disk, and that disk measures how much noise there is in the signal, because none of the signals we work with are pure sinusoids. There is always some noise which is added on to it. So the radius of the circle gives the uncertainty of locating this center, which means that this is the noise, the fluctuations in the signal. And the x1 and x2 are called the quadrature amplitudes of the signal. Okay. So now, given that, we now take the signal. I showed you the schematic of the cryostat earlier, and we now take the signal out of the cryostat and we can demodulate it. And to demodulate the signal, we have to essentially take a signal of the form x1 cos omega t plus x2 sin omega t, and we multiply. If you multiply the signal with cosine omega t and integrate it over a full period of the cosine omega t term, only the x1 term survives, the x2 term will go to 0. So you can compute what x1 is. That's how you measure. I mean, this is like your homodyne and heterodyne detection that is very commonly used in radio receiver sets. Okay. So you just use a homodyne detection to measure what x1 is. And similarly, you multiply it with a sine omega t, you get x2. Okay. So x1 and x2 can be measured very easily. And by measuring x1, x2, we can now get what the amplitude is and what the phase of the signal is. And as I will show earlier, show in a bit, it's the amplitude and phase which carry some very interesting information about our qubit. So this is the circuit. So to do this multiplication, we need these nonlinear devices called mixers, which basically multiply, and you take the signal and you multiply it with a cosine omega t, and at the output I put it as an LPF. It's an low pass filter which does the simple job of integration that I mentioned. Okay, and that gives you the x1 and x2, which are slow varying signals, and they can now be digitized. We do have digitizers which can sample these very slow varying signals quite reliably. Fast DACs are available, and we digitize those signals and we can process them for the amplitude and phase. This is the overall schematic for our measurement circuit. So now, what is the principle? How can we read out the state of the qubit using these resonator as a probe? So here is the schematic. You have the coaxial cable, the input line of the fridge that I showed. It goes to the device and comes out as another coaxial cable, the output line. So you input a microwave field and you output a microwave field, and you can now compare the amplitude of this output relative to the input and the phase of the output relative to the input. And that is what I'm plotting here. Okay. And you can see that a resonator usually has a Lorentzian line shape like this. Okay. And it has, it's actually, technically, this is a square root of a Lorentzian. The amplitude itself is a square root of a Lorentzian, and the phase has this tan inverse sort of characteristic. Okay. So this is what we observe when we measure the amplitude and phase of a resonator. Now, what happens when you couple a qubit to a resonator? As I said, a qubit has two states, ground and excited. It turns out that because the qubit and the resonator are like two coupled oscillators, the resonance frequency of the resonator shifts depending on which state the qubit is in. If the qubit's in the ground state, you will see that the resonance frequency of the resonator is basically this blue curve, and the peak here denotes the resonance frequency. And if the qubit's in the excited state, say you send a tone on the qubit resonant with the qubit, then the qubit gets excited, and the resonance frequency shifts. Now, if you monitor this resonator by sending a tone at this intersection here, what happens is the amplitude of both the qubit being in the ground state and the qubit being in the excited state, in both cases, the amplitude of the resonator output. Remember that what we are measuring is actually this amplitude of this B out tone relative to the input, right? So that amplitude will not change. But if you look at the phase will now have a nice separation, which will allow us to distinguish between the ground state and the excited state of the qubit. Okay. So this is how in the x1, x2, in the phasor diagram, this is what it amounts to. The length of this vector is the amplitude, and the angle it makes with this x1 axis is the phase. And what we see, this change in the phase essentially means that this vector is basically getting rotated. If the vector were originally here, it's getting rotated to this point. Okay. And again, I want to repeat that the signal coming out of the device is actually very, very, very tiny. And it is of the power of the signal is about attowatts. Therefore, we need to amplify it. And remember that the qubit information is actually in this direction, in the x2 direction, because x1 for both vectors, the x1 component is identical. So x1 is in some sense equivalent to the amplitude, and x2 is a measure of the phase. Okay. So we need to amplify x2 so that we can get the information about the qubit. So there are two kinds of amplifiers, phase sensitive and phase insensitive. Phase insensitive amplifiers amplify both x1 and x2 together equally, which means that this vector will basically extend diagonally to a larger length, which of course will increase x2, and you will get a better signal to noise ratio, better signal compared to what you have at the device. But that is not the optimal strategy, because we don't need to amplify x1 at all. We only need to amplify x2 because all the information about the qubit state is in this direction. x1 is identical to both states. So we need to do a phase sensitive or phase selective amplification, which is what we can achieve using what are called parametric oscillators and parametric amplifiers. I'm not going into the details of parametric amplification, but the key message is parametric amplification allows you to do a phase sensitive amplification. It's like this. So the x1 component doesn't get amplified, but the x2 component gets amplified. In fact, you will see that the x1 component gets de-amplified. So you don't get any information out of the x1 component. The x1 component is even smaller than what it was. So all the information in the x2 component can be obtained quite, with very good signal to noise ratio using such an amplifier. So this is the strategy that we usually employ so that we can measure these qubits. All right, that brings me to the last section of the presentation. Kirtipriya, do I have maybe like 5 to 10 minutes?
Yes, sure.
Yeah, all right. Again, let me repeat what the advantages of these devices are. As I showed, you can do simple photolithography and e-beam lithography, and thanks to the semiconductor industry, these two techniques are highly well developed. So fabricating these devices is very easy. That's one very attractive feature. And microwave regime is very well established thanks to radio and radar technology. Superconducting artificial atoms, I also mentioned that these are hundreds of microns in size, right? The size of the atom is usually proportional to its dipole moment, okay, roughly. So these atoms being so big, if you want to compare, the dipole moment of these microwave superconducting artificial atoms is going to be huge compared to, say, a natural atom coupled to laser fields, which means that we can actually achieve very large coupling to these microwave fields. Now, why is that important? That is both a boon and a bane. It's a boon because it allows you to do these gate operations. Usually the gate operations are inversely proportional to the strength with which the atom couples to the field. So gate operations can be done extremely quickly, but the same coupling also coheres the qubit. So you need to control the coupling in a clever way so that you enhance it when you want to do a gate operation, but turn it off when you want to preserve the information in the qubit. And this is what people routinely do using tunable couplers. Okay, so this advantage, and using all these strategies, the coherences, the first qubit that I mentioned, which was measured in 1999, had a coherence time which was less than a nanosecond. Okay, but they have steadily improved, and this is actually quite outdated now. The information there is more information between 2015 and now, but the state of the art is we have about a coherence of roughly 200 microseconds. This is not great, but thanks to the strong coupling, the gate times are a few nanoseconds, which means we can do about a few 100,000 operations before the qubit information is lost. But this is not much. A few 100,000 operations is not even close to what our classical computers, our Intel i9 and i7 processors can do with their 3.2 gigahertz processors. Okay, so the clock speed is what we are talking about here. This is not much, but even with these sort of noisy intermediate devices, people have reached quite a distance. So these are some of the achievements that superconducting circuits have made in the last few years, last couple years, in fact. So Google is a leader in the traditional programmable quantum computers, and they are leading with 50 qubits and trying to go to 100 qubits quite soon. IBM is another giant which has demonstrated 72 qubits, and they have a roadmap for 1,000. And D-Wave is another company which is actually working with 5,000 plus qubits, but they are not a programmable quantum computer like Google's or IBM's. So that's why it's called an eigensolver. And this is designed to tackle some specific problems like optimization problems. And they are doing quite well. And to compare, since we are talking in the Indian context, our neighbor China, there is an academic group by Professor Jinwei Pan who demonstrated 64 qubit processor and demonstrated a quantum walk on this processor. And this is by far the largest number of qubits. This is of course comparable to a company like Google and IBM, which in itself is a big achievement. And of course, no academic group that I know of in the world can support such large number of qubits. So China is investing a huge amount of money in this exercise. India has started late, but they are now investing quite a bit in this technology because this technology is not transferable. It has strategic interests in mind, so we cannot really borrow this technology and import it from elsewhere. And I want to now touch upon some interesting application. So microwaves are not, I spoke about quantum computation and what has been achieved so far. There are other applications of microwaves in the form of surface acoustic devices. Surface acoustic devices are not new at all. In fact, from the 1970s, they have been quite regularly used in RF signal processing. Mostly in the L and S bands. Okay, And these are basically interdigital transducers. Remember this interdigital interlocked finger structure that I showed earlier? These devices, if you lay them out on a piezoelectric substrate and you supply a microwave tone to one of the electrodes and ground the other electrode, the microwave energy will now be converted into a surface acoustic wave of the same frequency propagating on the solid, on the piezoelectric substrate. But the surface acoustic wave travels at the speed of sound, and speed of sound is 100,000 times smaller than the speed of light. So what that means is the frequency of the excitation and the frequency of the emitted surface acoustic wave are the same. And because the speed of sound is so small, and nu times lambda, that is frequency times the wavelength, is always equal to the speed of the wave, right? Because of this, the wavelength of this surface acoustic wave is very, very small. It's 10 to the power of 5 times smaller compared to that of a light wave of the same frequency. So to give you some concrete numbers, if you have a frequency of 3 gigahertz, the wavelength of sound is 1 micron of the same frequency, whereas the wavelength of light for the same frequency will be 10 centimeters. So it's a factor 100,000 smaller. What this automatically leads to from an engineering perspective is it will compactify the geometry. If you want to make an RF filter, a multi-stage RF filter, it's not really possible using standard LC components. You have to use transmission lines and all these things, but even otherwise, if you use a SAW RF filter, it's extremely small in geometry, a few millimeters at best. So this is very compact, and this has been used regularly. If you open up a cell phone, you will find these SAW RF filters in each cell phone. And this is almost 40-year-old technology now. And interestingly, you see this 1 micron is actually very close to infrared wavelengths. And in fact, if you go to slightly higher frequencies, you will touch visible wavelengths. So in principle, surface acoustic waves, which are excited using microwaves, have the same wavelength as visible light. So there have been proposals to actually use this as a sort of intermediate to convert microwaves to optical. Now, why is that an interesting application? Because microwave to optical conversion is useful in transmitting quantum information. If the processor, as I showed, superconducting circuits are leading, and the quantum computer may in fact be a microwave device, but to transmit this microwave information, it's always better to transmit using optical signals along optical fibers and all these things, because microwave signals cannot go very long distances. You need to have frequent these towers, like cell phone towers. You need to have towers at different places, and that's a problem in the quantum scenario because you will lose information from tower to tower. I'm not going into the details, but you cannot do the same strategy in the quantum case. So you have to do some conversion from microwave to optical and transmit that information. So this may be a potential application. But for the quantum domain, this piezoelectric superconducting circuits on a piezoelectric substrate, instead of using say silicon or sapphire like earlier, if you use these piezoelectric substrates, you can study some very interesting physics. For example, in all of light matter interaction, that is, if you take a natural atom interacting with visible light, the atom is a few angstroms, which is 0.1 nanometers, and the visible light is hundreds of nanometers. So the visible light is, the wavelength of the light is at least 10,000 times more than the size of the atom. Whereas if you use surface acoustic waves in the place of light, the wavelength of the light will actually be 1 micron when the size of the atom can be 100 microns. Now this cannot be done using light, meaning you have to convert electromagnetic microwaves into surface acoustic waves, And if you can couple these surface acoustic waves to these superconducting artificial atoms, you can study an entirely new regime of matter-light interaction where the matter, that is the atom, is much, much, much bigger than the wavelength of the light. And we did experiments. This is actually data from a Nature Physics article that I, co-authored with my PhD student during my postdoc. And you can see some very interesting features. So for example, what I show here in this bottom left graph, so on the top is the schematic where these are these IDTs that I talked about, the surface acoustic wave transducers that I showed in the previous slide. These will launch the surface acoustic wave, and this device here is the qubit, which has these two Josephson junctions, and it has a capacitor in the same geometry as the IDT, and that will pick up the surface acoustic wave, and you can measure it. You can essentially probe it with sound. And when you measure its spectrum is no longer a single line shape like what I showed earlier. Like the resonator, it had a nice single Lorentzian. This is no longer a single Lorentzian, it's a multi-pronged Lorentzian. And this is the frequency domain. If you do the inverse Fourier transform into the time domain, you will see that this doesn't have a simple exponential decay. Those of you who remember Fourier transforms, an exponential decay in the time domain corresponds to a Lorentzian line shape in the frequency domain, the Fourier transform of the exponential. So in the same way, this is no longer an exponential, and it has these sort of characteristic peak structure. Okay, this is some interesting physics of the giant atoms that I mentioned. And this is another comparison. So this is just showing you in pictures. This is the Lorentzian line shape. Concentrate on this. The top picture is for a small atom interacting with light. The peak from 6.2 to 6.4 gigahertz, it's a nice Lorentzian looking peak. And if you measure the time domain profile of this peak, it falls along a nice exponential. Whereas the giant atom, this is what we usually have when light interacts with matter. That is a small atom interacting with a long wavelength light. Whereas if you reverse the roles, you have this very interesting non-Lorentzian line shape, which also translates in the time domain to a non-exponential decay. All right, so now coming to the challenges. First challenge is it requires millikelvin temperatures, which means the cost of setup of these microwave superconducting circuits is rather high, and long-term scalability of these devices is in question. Now I will show you a few pictures to tell you why this is so. And the peripheral components, such as the interconnects, the cables, the attenuators, the circulators, isolators, and all these microwave components that we use, they are usually bulky and they are desperately in need of compactification. And relatively, we are left with about 10 gigahertz of bandwidth, and that's a narrow band, because if you compare optical bandwidths, those are huge. Whereas here you have very narrow bands. So as you increase the number of qubits, this can lead to frequency crowding. Okay. And similarly, right now, all the control electronics is at room temperatures in these large racks that I showed you, occupying a whole room. We need to miniaturize them and ideally also put them probably at a lower temperature so that the noise coming from these electronics is also reduced. And the points in italics here are more related to the coherence of these devices and what quantum computation tasks people can have not done so far. But we'll leave that to the quantum physicists to figure out. But in the electrical engineering context, these bold case points are what we are interested in. Now, scaling up. So I said all these components are very bulky. So here is a picture from Microsoft showing the insides of their fridge, which has maybe 30 qubits maybe. And you can see that the wiring is crazy. Now this is 30 qubits, and I told you that the practical number that is useful is 1 million. No sane person will imagine that an architecture like this will be straightforwardly scaled up to 1,000,000 qubits. Obviously not. You cannot deal with this maze of wires even at the level of 100 qubits or even 1,000 qubits. So reaching 1,000,000 qubits with the same strategies as we have today is rather impractical. And secondly, what I show here is a measurement rack, the top one, and here is another equipment that we have in a rack next to it. These are the equipment we need to control 1 qubit. Okay. Now these are boxes that we buy from companies like Zurich Instruments is a startup which was recently acquired by Rohde and Schwartz, and Rohde and Schwartz, Keysight, and all the usual Tektronix and all these. I have, you name the company, I have equipment from them. But these are boxes which are quite useful in the radar and radio contexts. But when you talk about quantum computation, the number of input lines and each input line hooked up to a box like this, you cannot even imagine that each qubit requires 4 such boxes. And this is the rack that supports the electronics for 1 qubit. How will we scale this up to 1,000,000 qubits? Obviously, people are working out, for example, this box here can control up to 4 qubits or say 3 qubits. It's one box that controls 3 qubits. So that's an improvement, but that's still not nearly enough to do 1,000,000 qubits. And then the microwave components themselves, as I said, this is a 2 rupee coin, which is roughly, you know, a 3/4 of an inch in diameter. You can see that all the microwave components, including the smallest of them, which is the simple humble attenuator, they are comparable in size. And some of these circulators and isolators and directional couplers are even bigger. And this is a coaxial cable. The connectors of the coaxial cable, they are a fair chunk of this diameter, which means if you have 1,000,000 qubits, you are going to have these million SMA connectors. I mean, 1,000,000 SMA connectors are going to occupy a hell lot of space, because it's like putting 1,000,000 of these 2 rupee coins, or maybe one of the old, if you remember the 25 paisa coins, they are maybe 50% of a 25 paisa coin size. So these are quite big. I mean, you can't imagine. So miniaturization of microwave components is the challenge, and that can be done by microwave engineers. So in conclusion, I want to conclude with these few points that I touched upon. Microwave technology has brought superconducting qubits this far. So the questions are, can it take it beyond? So for that to happen, miniaturization of microwave components, and not just the devices, but actually the passive and active control and peripheral components around the device, those have to be miniaturized also. And there are open questions in even packaging. How do you package 1,000 qubit device? How do you package 1,000,000 qubit device? The kind of wires that have to, the transmission lines are very bulky. So how do you scale them down? Or how do you scale the number up? Microwave engineering is going to play a very crucial role in achieving these breakthroughs in all these questions. And that is the larger message from my presentation. Thank you.
Thank you. Thank you for the great talk. So we are open to questions, and a couple of questions we'll take now because we have, I think, around 5 to 10 minutes left. So
Yeah.
the first one is, so when you say you used silicon as a substrate for your LC oscillator and the Josephson junction, can we use some other substrate? What are the constraints when you go for these lower temperatures?
Oh,
the
so actually, the earliest substrate that was used was sapphire. Okay, sapphire is a very good dielectric and very mechanically very stable. So you need, basically you need the mechanical stability, because you should not have the substrate crack and break at low temperatures, and it should have good dielectric properties. Silicon, pure silicon, intrinsic silicon at such low temperatures has very good dielectric properties and very few losses. So it works very well, and it's the most abundant element, right? So getting pure silicon is actually quite easy.
Okay.
And
Next
other
one.
substrates are used, but very rarely. Silicon is the workhorse these days.
Great. So next one is, how efficient do you think it will be if we want to have so much of cooling to be done for implementing the qubits?
That's a very good question. The thermodynamics, the thermal cost, that's what you're asking about. That is the cost of actually maintaining such a device. Well, thankfully, it is not scaling linearly or even, as a power law. It's scaling quite less. So far, the cost of making a fridge or a cryostat that can cool 100 qubits and the cost of making a cryostat that can cool 1 qubit is only 20-30% more probably. It's not the cryogenic aspect of it which is expensive. The RF engineering is much more expensive. For example, the wiring that I need to do for 100 qubits will cost me a ton of money. It's not so much the cryogenics.
I think another question related to that is, so then do we need to go for the LNAs, all the other microwave operation in the cryogenic temperatures? Is it necessary?
So, well, that is to improve the coherence of the signals and to remove the noise. So that is the main criterion behind going to low temperature electronics, and also to miniaturize. Ultimately, I mean, if I have to, envision my dream device, it would be basically a small chip like the Intel processors, which has all these interconnects which are nicely engineered, and I have control electronics at the same temperature right next to it, so that the transmission of these signals doesn't take tens of nanoseconds, and the round trip time, because we also want to do feedback control, right? Ultimately, we have to, I did not mention all these error correcting strategies, but if you can do some stabilization and error correction and all these, you don't want a lot of time to go in the closed loop control of the system. So the round trip time should be small. Right now it is a few tens of nanoseconds, or a few, even going up to a sub microsecond level, which is not ideal. So that those are the criteria going into low temperatures, but the wiring and other strategies have to evolve accordingly.
So one question from my side. So when
Yeah,
you see
please.
so you told that we need a tone for exciting the oscillators. But then again, the
Yes.
coherence is an issue you told. So what are these phase noise characteristics of the tones you expect, or what should be the frequency stability of these tones? How
Oh,
pure of
that
a
is.
sinusoidal tone it should be?
Oh, yeah. So right now we have extremely pure, they are the purity of at gigahertz, right? At gigahertz frequencies, they are stable to less than a hertz. So they are extremely narrow line width. Okay. So these are extremely good sources, and the phase noise characteristics of, you don't have to spend tens of thousands of euros and get a very sophisticated source. Something of, reasonably, say a few $100, you can still get a source which is very, very, very coherent for these applications. There is no problem. I'm not talking about noise coming from the sources and their fluctuations. I'm actually talking about the environmental noise, like the electromagnetic environment and the temperature, thermal noise, infrared, all these things. Those are the bigger problems.
Okay, but I thought when you say you want to excite using a tone, and basically it's more like a difference between the shift of your qubit and your exciting tone. You're seeing the amplitude and the phase characteristics. So wouldn't it matter if your actual microwave tone itself is going to be shifting in frequency? So how
Oh,
will the
no. Okay. Yeah. So just to give you a number, the frequency stability of my tone is sub hertz, I said, right? at gigahertz, I have sub-hertz stability, and the line widths of these resonances, right, those are tens of megahertz. So the tone that you are sending onto the device is at least a billion times more stable than the qubit itself. There is no comparison.
Okay, that's what I wanted to know. Yeah.
Yeah. These are much more coherent. Classical technology is excellent. Yeah.
Okay, I think the last question we'll have a non-technical and it's more like a futuristic question, a general question. So, how India is now contributing towards this quantum field, and what are the various activities happening in India related to this field now?
So you can say that superconducting circuits, there is activity, but there are only 3 people in the country. I'm one of the 3 working in this area. Worldwide, so all 3 of us, we studied abroad and we learned all the skills there, and we are trying to apply them here and try to get the first quantum computer built in India. So one of the groups is in TIFR, which is the senior most group, which is only 7 years old. It's not that much senior. And then we have 2 groups in IISc, Professor Vibhor Singh in physics department and myself. So Vibhor joined about 5 years back, and I joined 3 years back. So we are still in the early stages. So we have projects sponsored by the government is investing heavily in this technology, but they are only 18 years late. But that is still it's never too late, right? So we are looking at the positive side, and they have invested quite healthily. So hopefully in the next few years, we can scale up our operations, and we are currently at around 4 to 8 qubits, not too far behind if you think about it, but scaling up requires a lot more manpower, because 3 people cannot achieve what, say, a company like Google with, if you look at a paper from the Google group, there are at least 25, 30 authors. That's just the Google group, and that's one group, subgroup. The entire team is several, hundreds and hundreds of people working. So manpower is what we are currently, facing a crunch of. And once we get more people, we can accelerate. And quantum technologies, all aspects of quantum technologies, not just now, but for the last 15 years, people have been working on different aspects of them. But to make a mark, these are not, the bread and butter sort of research that we were used to in the earlier days with smaller investment. These have to be mission mode projects, which need massive investment and in-house indigenous technology building from scratch. It's like, we have to approach it with the same sincerity and conviction as the space program and the nuclear program that India pursued.
Thank you so much for all your answers, and it was a great talk. You started from the basics, and you have nicely explained to the recent work that has been happening so far. So once again, I thank you for accepting our invitation to give a talk in
Thank you.
AP-MTT.
Yeah. Thank you.
Yeah. Mahesh, sir, do you have anything to say, or can we close the session?
Yes, madam. I have one question. Can I ask?
Sure. Yeah.
Yeah.
Oh, thank you. Thank you very much for the nice presentation, sir. Sir, when you talk about miniaturization of this microwave components or transmission lines, how much percentage miniaturization is possible, or you're predicting any kind of that?
No, that's a big challenge. So it is a very big challenge. I mean, there are microwave ICs. It's not like they are not there, and people are trying to push the boundaries. It requires you to investigate materials and lots of things. So it's not such a straightforward thing. And I'm not a microwave engineer per se. I only use the technology to do physics and to apply it to quantum computation. but it is challenging because you have fundamental limits. But for million qubits, right, we don't really, if we can reach a million qubits, we already have a quantum computer which can do wonders, which no classical computer, not just now, not in the past, nothing classical can be built to surpass it. So it already does wonders at that point. Even with 50 qubits, people demonstrated what is called quantum supremacy, which by itself means that something that a classical computer cannot do with some equivalent in any time, you give as much time as you want, more than the age of the universe, which is some 10 to the power of some 14, 17 seconds or something. You give even the age of the universe, the computer cannot compute, the classical computer. So people have already demonstrated that using 50 qubits. So with 1000, we can do a lot more. There are problems in biology, in chemistry, which are waiting to be, solved, which currently are solved using some crude techniques, using some classical algorithms and some approximations and all these. But they study a toy model, which is much, much, much smaller than the actual molecule or its chemistry. So these sort of applications require bigger computers. And for that, if you want to, believe in superconducting circuits. So I did not actually mention the other technologies. All the technologies that exist today suffer from this problem. There is no technology which is mature like the superconducting circuits and is also scalable at the same time. So all the technologies are suffering from this compactification problem, but engineers have always found a way around it. So I'm going to put my faith in engineers and say that we will conquer it eventually.
Yes, sir. Thank you very much, sir. So that means it has got a lot of opportunities and applications.
Yes, and a lot of the points that I raised today are actually open questions. There may or may not be people working on it. So RF engineers among you who are interested in taking up some of these problems and colliding them head on, welcome.
Thank you very much, sir. Thank you very much for your talk. And on behalf of IEEE AP-MTT Bangalore chapter, I would like to thank you again for accepting the invitation, and thank you, Kirti Priya madam, for arranging
Thank
this.
you.
Thank you very much. Yes.
Yeah.
Thank you, sir. So we'll close the session officially. Thank you so much.
All right. Thank you.